This is recording. We'll put it on YouTube like all the other ones. I'm going to go through these problems that were from chapter 5, 6. Oh, I forgot one. So you're all good. And if you need to leave, it's totally cool. All right. So let's start here. A constant force, which in our class, all forces are constant, is applied to a vehicle, an object, which causes an acceleration of 9 meters per second. What will the acceleration be if we double the force? Well, this one's easy, but so from Newton's second law, we know F is equal to ma, or A is equal to F over m. And therefore, if we double our force, we double our acceleration. That's pretty obvious. If we double the mass, we can see here that we'll get half the acceleration. So if this was 2m instead of m, it would make our acceleration half as much. If both the force and the object's mass are doubled, so we end up with 2f over 2m, obviously, nothing changes. And then finally, if we double the force and we half the mass, then what we get is 2f over m to the half, but the half would pop up, so we get 4 times the acceleration. That one's pretty simple. Mostly I assigned this one because I wanted you to reinforce F equals ma, Newton's second law. As we go. All right, so the following problem: in a lab, you propel a cart with 4 known forces, so 4 times 4 different forces, and you detect the acceleration. Now, we want to determine the mass using a slope line. And whenever we have a linear trend line, which we're assuming, y versus x, and we have some line that looks like this. If this is linear, then y is equal to mx plus b. B is basically wherever this thing intercepts the y. I'm assuming you all know that. And m is the change of y over the change of x in our function. So if we wanted to find F equals ma, and we wanted to find the mass, we would divide through by a. We would want to graph on the y, our force, and on the x, a, so that our slope is our mass. And then if we look at this, we can drag down which ones go which. You guys, I think, have 5 different ones, but we're going to graph F versus A to get mass, and mass is our slope. That one's not too bad. Another data point that we could add is, in this case, and it's not usually true, but we expect that if the force is 0, the acceleration is 0. So we can add 0, 0 to our graph if we want. And then finally, when we graph this, and this is shown, your slope, this is y is equal to mx b. Since we assume when x is 0, y is 0, or when a is 0, f is 0, we get a slope of 0.56. For an F versus A graph, that gives us the mass. So this isn't too bad. I just wanted to remind you about how we do graphing, just so you a little bit of reinforcement. It's pretty simple. Now we're going to get to harder stuff. So those first 2, just stuff I wanted you to think about. So we have a person or a thing, and they're in an elevator that is descending at 11 meters per second when it comes to rest. Okay, so what we need to understand in this, and this is why we've been doing all these free body diagrams. We're in an elevator, and this is our Zach. And he has a weight that is mg. And he's standing on a floor, so we assume there's a normal force. But he's in the elevator, and the elevator itself, okay, is basically coming to a stop. So it has an initial velocity of 11 meters per second, and it has a final velocity of 0, stops. We don't know how far it went, but we know that the time was 3.5 seconds. And what we need to be able to figure out is what is A here, okay? So we need to find the acceleration, which will be upward, even though he's traveling down. Our acceleration, it'll end up being negative. I'm going to actually assume that y, let's call it, is down. That means that our A is going to be negative because as it drops, it comes to rest. So it's slowing down. Now we know that V final is V initial plus AT. And from this, V final is 0. We get that V initial is minus AT. And A is V initial over minus T, which is 11 over minus 3.5. And it's totally okay for our acceleration to be negative. Time can't be, but acceleration can be. So 3.143 with a negative sign is our acceleration for Zach. And what we want to know is, what is Zach's weight before the elevator starts braking? Well, his weight is mg, and they gave me, you probably have different numbers, they told me that he has a mass of 85 kilograms. So this, before he starts braking, is mg, which is 85 kilograms times 9.8. So 85 times 9.8 is 833 newtons. Remember that weight is your mass times your times gravity. However, while this thing starts to brake, what's going to happen is actually we're going to ignore the normal force because it's internal to the elevator, and we'll take the whole thing. So what we get here is we get that MA is equal to mg, sorry, I did that wrong. We do need his normal force. His normal force is actually what we record as his weight. The normal force is actually what a scale would measure. So what we're going to do is we're going to take this to be MA, which is going to be negative, is equal to the weight mg minus the normal force. Therefore, normal force, if I move it over and move this over, mg plus ma. Add ma to both sides, add normal force. This is what his apparent weight is. Okay. Now we know our acceleration is 3.143. This negative sign is due to this negative sign. So this is actually 3.143. And I get that his apparent weight is his mass times g plus a, which is 85 times 9.8 plus 3.143. 9.8 plus 3.143 times 85, I get 1100 newtons. And hopefully I did that right. 1100 newtons. Okay, what they've done in this solution right here that they're showing is that is the acceleration of the elevator. However, what they don't tell you is that we actually do need to measure the normal force, not the weight. The normal force is your apparent weight. That's why when you go over a hill, you feel like you get weightless because your normal force disappears on the seat. As you sink under, your normal force increases because you drop into the seat, and your weight, you feel like you weigh heavier. All right. Yeah. And there is in our textbook a bunch of elevator problems. If you want some more on that. Now, this is a friction problem. More importantly, it's a static friction problem. So what we need to remember is when we have static friction, the magnitude of the static friction is said to be minus mu s, the normal force. It's a variable force, which means until it hits a maximum, it will basically reflect any force acting on it. So it'll act against any force until you hit the maximum, and then it goes away. The negative sign means that the vector opposes a net if there was no friction there. So you add up all the forces and figure out which way it should be opposing. That's not always obvious. Thankfully, in this problem, it is. So we have Bob pulling a 30-kilogram filing cabinet with a force of 200 newtons, but it won't move. And we're told the coefficient is 0.8. So mu is 0.8 in this case. We have a filing cabinet that is being, this is a 30-kilogram filing cabinet, and he's pulling with a 200 Newton force. Now, if we look at the free body diagram, everything that's on a surface has a normal force. Everything has a weight. There's a force of 200 newtons, and we're trying to move it in the X. It can't move in the Y. It actually can't move in the X unless we overcome static friction. But that means that in order to balance this, our static friction force has to be opposing the only force in the X. So we write MAY is N minus the weight, which is mg in this case. And we write MAX, don't forget this. MAX is F minus F of static friction. These are both 0 because we were told that it wasn't moving and it can't leave the surface. This tells us that the normal force is mg, which in turn tells us that the force of static friction is mu s mg. Therefore, the force of static friction is equal to the force from there. We're asked to find the magnitude of the friction force. So instead of doing this, let's just solve it for mu mg. We were told mu was 0.8. Yours might be different. File cabinet is 30 kilograms and G is 9.8. So I get 0.8 times 30 times 9.8. I get 235. Sig figs only 2, it would be 2.4 times 10 squared, but they just went with 200. So they just rounded it to 1 sig fig, really, which is weird. But oh, I'm so dumb. You guys, I'm sorry, it's late tonight. Had a long day. The static friction force right now is actually, this is the magnitude of the maximum static friction force. The static friction force while he's pulling on it is simply going to oppose his force. So it's going to equal whatever force you pull on it. So the static friction force is equal to the force in order for us to have 0 acceleration in the X. And therefore, since he pulled with 200 newtons, we get 200 newtons. I'm dumb. And you know what? Maybe that's why I gave this to you. I don't remember. But yeah, it's a good question to make sure that you understand it's not the maximum static friction, it's just whatever force is acting on it. So hopefully that makes some sense. All right. A 1,500 kilogram car skids to a halt on a wet road where the coefficient of kinetic friction is 0.16. Now, if it leaves 45-meter long skid marks, we want to know how fast was its initial velocity. So first of all, the car is traveling on the road and it has a normal force, it has a weight, and it starts to brake. So there is a force of kinetic friction, since it's already moving, that opposes the direction that it's traveling. We're going to assume it's traveling in that direction. So we need to figure out what its acceleration is. If we do MAY, n minus mg, that's n minus mg. We know that's 0 because we're assuming the car won't leave the surface, and n becomes mg. Our force of kinetic friction is mu k normal force, and it's the only force in the x direction, but it's negative because we're choosing x to be positive. That way what we get is a negative acceleration. If I divide both sides by m, my acceleration is negative mu k, if you want to call it mu k, or just in this problem, it's fine, is negative mu k. However, I'm told that there's 45 meters of skid marks. So from where we start measuring to 45 meters, we know that V initial, actually we don't know how fast it was traveling. We know that the mass is 1,500 kilograms, and we know that mu k was 0.16. We want to find V initial. V final is 0. It comes to a halt, meaning it stops. X initial is 0. X final is 45. We don't know the time, but A is minus mu kg, which is minus 0.16 times 9.8. 0.16 times 9.8, 1.568 meters per second squared. Now, if we don't have time and we don't need time, the only equation that we want to use is the following. X final minus X initial is V, no, that's not the one we want to use, sorry. Being done. V final squared minus V initial squared is 2A X final minus X initial. Now we want to solve this for V initial. V final is 0 because it comes to a halt. X initial is 0 because we chose it that way. There's a negative sign. Let's move that over. So negative 2A X final. And then we're going to take the square root of both sides. So V initial is square root of negative 2 times negative 1.569 or 68, I'm sorry. 45. What we get, those negatives are going to cancel. So 2 times 1.568 times 45. Don't forget to take your square root, and I get 11.9 meters per second, maybe 12. I'm not sure how many sig figs. I think they may only want 2. So 12 meters per second. So this problem, you have to find A from the friction. Drawing a free body diagram may not be totally necessary, but I find that it helps to actually just get the acceleration. Once you have it though, you switch into constant acceleration equations and solve for that. And I want to make sure that you guys know how to do that. And it, did I forget something there? Nope. However, if you want to pause this and see this, this is essentially what they did. This is what they got. And then they solved it. And since you can pause the video, you could pause it here and look at this. But it's essentially what I did. And yeah, so hopefully that's pretty straightforward. Now, this is something we haven't talked about a lot. We may talk about it more later with certain problems, particularly ones we have torque. But in this problem, we are in equilibrium. And what that means is nothing's moving. There's no x acceleration, there's no a acceleration. We're told that there are two ropes holding an 1,100 kilogram steel beam, one at 20 and one at 30. So let's just draw that really fast. This is 1,100 kilograms, and there's two beams here. This one's at 30 degrees from the vertical, and this one's at 20 degrees. And this is T1, this is T2. And we need to find T1. Now, you might be thinking to yourself, I don't know how to find this. Well, what we do know is if we draw a free body diagram and we break these up. Now, for T1, this is T1 in the X, and this is T1 in the Y. And if I draw these with, say, a red pen, this would look like this, and this one's going to look like this. This is T1 Y, and this is T1 X. This is the cosine of this triangle. This is the hypotenuse, is T1. So T1Y is the cosine of the magnitude of T1. And T1X is T1 sine. It's a little different. Now, for T2, it's the same thing, except remember that they have different angles. So this is T2 cosine of angle 2, and this is T2 sine of angle 2. Now, when we draw this free body diagram, it has a weight, mg. It has a tension and another tension. So it has T1y and T2y. And then it has T1x and T2x. Now, when we draw this, we know that do Newton's equations. max is, and I'm going to choose, although it doesn't really matter which way you choose in this particular problem, since they'll be 0, but we need to choose it one way or another. I get T2x minus T1x is equal to 0. Then in the y direction, I have may is T1y plus T2y minus mg is equal to 0. They're both equal to 0 because they are in equilibrium. So let's go to a new page, and I'm just going to use this part of it. So I have the T1 cosine of angle 1, move this over, is equal to T2 cosine of angle 2. And angle 1 and angle 2 were 20 and 30. And then I have mg is equal to T1 sine theta 1 plus T2 sine theta 2. And my mass was 1,100 kilograms. So all I've done is I moved that over so that mg is equal to 2 and that over. Now, at this point, what I'd recommend is actually doing a substitution, okay? So I get that T1 is T2 cosine theta 2, move cos theta 1, cos theta 1. So this goes away. And then substitute that in here. And we're going to solve for, whoops. Can't write tonight. We're going to solve for T2. Now, doing a bit of algebra here, what we get is we get that mg is equal to T2. Sine over cosine is tangent. Cosine theta 2 tangent theta 1 plus sine of theta 2. And remember that therefore T2 is mg over all this stuff. And I hope that truck doesn't start getting too loud. I'm sorry, my neighbors. Now, I'm going to just put this in my calculator. This is 1100. This is 9.8. 1100 times 9.8. So 780 divided by cosine of 30 times sine or tan of 20 plus sine of 30. And I get 0.8152. So this tension is 10,780 divided by that answer. I get 13,223 newtons. That's T2. Now T2 is 13,223, and I put this in here, then T1 is 13,223 cos of 30 over cos of 20. So 13,223 cosine of 30 divided by cosine of 20. And I get 12,186 newtons. Wow, what did I do wrong there? They're annoying me. Yeah, that, oh, did I flip something? It looks like I flipped my, no? Oh. Okay, so let me double check myself. This is to, did I think oh, I'm so sorry, you guys. All this work for nothing. I flipped my cosines to sines. You got to be careful when I flipped these. I totally flipped my sines, sine and cosines, because I'm dumb. Blah, 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 blah. Those are still the same. However, so the y, T1y and T2y, these are the cosines, if you remember. And when I wrote them down, I just wrote them backwards. Cos theta 1, cos theta 2. This is T1 sine of theta 1 and T2 sine of theta 2. And that means T1 is T2 sine theta 2 over sine theta 1. Plugging that in there, and we get that mg is T2 sine theta 2 over sine theta 1 cos theta 1 plus T2 cos theta 2, distributing mg. This is sine over tangent, and this is, so sine over sine of 2 over tangent of 1 plus cos of 2. So T2 should be 1100 times 9.8 divided by sine of 30 divided by tan of 20. Divided by sine of 30 divided by tan of 20 plus cosine of 30. And I get 4813 for my T2. Plugging that in here to get T1, well, here to get T1, I get 4813 sine of 30 over sine of 20. So times sine of 30 divided by sine of 20. And I get 7,036 newtons. If I round this, I get 7,000, which is what they got. For T2, I get 4813. While I would like to say that I purposely messed up the cosine and sine, just to remind you to make sure that you do it right from the picture. I actually just totally goofed when I moved to the next slide. So just remember that this angle is where normally we would have it like this, and this would be our hypotenuse or our T1. So this would be our T1, and this would be T1 sine of our angle, and this would be T1 cos of our angle. But because this angle is actually turned 90 degrees, this becomes our T1 cos, and this becomes our T1 sine. And then just don't mess it up when you put them in here. All right, we're almost done actually. Sam has a mass of 75 kilograms, and he takes off across a level surface on jet-powered skis that have a thrust of 230. The coefficient of friction with the snow is 0.1, and his skis run out after 8 seconds. So we want to find his top speed. Now, everything's blocks. The one thing that might throw you is this 230 newtons is a force pushing him that way. He's going to have a weight, he's going to have a normal force, and there's going to be friction. We're told that there's a kinetic friction. So there's going to be a friction force here. Now let's redraw this. N, our weight is mg. The force was 230 for me. And my friction force is mu n. Mu was 0.1, m was 75 kilograms. We don't need to know the time yet, but we will eventually. So the time was 8.0 seconds. But let's find A first. So MAY is N minus mg. Since he doesn't leave the surface of the snow, we assume N is mg. Our force of friction, kinetic friction, is mu mg. MAX is force minus mu n, which is force minus mu mg. Our acceleration, if we divide through by m, is force minus mu mg divided by m, which is 230 minus 0.1 times 75 times 9.8, all divided by 75. So his acceleration is 230 minus 0.1 times 75 times 9.8, and then divide the whole thing by 75, and you get 2.087 meters per second squared. Now, we want to know what his top speed is. So at this point, x initial is 0, x final is unknown, v initial is 0, he starts from rest, v final is unknown, but that's what we want. Our A is 2.087, and our T is 8 seconds. That came from the problem. So I'm doing this right here so I don't have to flip slides. We were told that after 8 seconds, he ran out. Now we don't know x final, so we don't want any equation with x final, and the only one that doesn't have x in it is this one. This was 0, so this is 2.087 times 8. And 2.087 times 8 is 16.7, or 17 meters per second, if we do 2 sig figs. Okay. The reason why we're doing 2 is we have 0.1, and technically this is only 2, and this is 2. I would argue that this is actually 3, but if it wants 2 sig figs, give it 17. If it wants 3, give it 16.7, and I think it will take 16.7. Now, how far has he traveled when he finally comes to a stop? And this problem's a little bit harder. First of all, we need to figure out in that first time of 8 seconds. X initial, we didn't know X final. V initial was 0. V final was actually 16.7. Was actually 693. And A was 2.087. And then in the second batch, he's going to have a new acceleration. And he's going to travel a new distance. So I'm actually going to figure out how far he goes in the new one. V initial for this part is the following, and V final is going to be 0. I'm just going to treat this as its own problem. So I'm going to call it X initial 0. X final is unknown. Note that this time, normal, weight, and force of friction only. There's no more force anymore because we ran out of fuel. What that means is MAX is equal to negative mu n, which is negative mu mg. So AX is negative mu g. Mu was 0.1, right? So this is negative 0.1, 9.8, which is negative 0.98 meters per second squared. So we know our A here is negative 0.98, and the time is unknown. But we want to find X final. And we need to find X final here as well. We know the time, we know the acceleration, we know V final, we know V initial. We can find it any way we choose. I'm going to go with V final squared minus V initial squared is 2A X final minus X initial. X initial is 0, V initial was 0. Divide through by 2A. And we get 16.693 squared over 2 times 2.087, not G. This is our acceleration in the X direction. Then we have to add this X final. Now this X final, we again don't know T, so let's use the same thing. But now we don't know V initial, so V final squared, V initial squared is 2A X final minus X initial. For this batch, X initial is 0, V final, and what we get is that X final is negative V naught squared over 2A. Okay. A is going to be negative this time. So this is negative 16.693 squared over 2 times the negative signs are going to go away because there's a negative and a negative. 2 times 0.98. What are you doing? Stop. All right, and then we're going to add these two X finals together. So 16.693 times 16.693 divided by 2 times 2.087 is 6676 plus 16.693 times 16.693 divided by 2 times 0.98 is 142.17. And so his total is 208.9, so 209 meters. 210 meters is what they're getting. And somehow, I don't know why they're getting 220, but I guess it will take any answer in between the two. I'm not sure. Yeah, they're getting some weird stuff going on there. I get 209 meters. Check it for yourself and see what you get. Let me know if it's giving you an issue. But I might have rounded somewhere that I shouldn't have, and that's why. Rounding can lead to significant errors. But to go back through this, for each point, the point when there's a force, find the acceleration, and then find the final velocity after 8 seconds using that acceleration, and then find how far it went during that 8 seconds, and then how far it goes before it stops, and put them together. It's not too bad. These answers look weird. All right, this one we talked about in class, and I was really worried about this. Now we're going to, what's going on here is we have a book, and you're holding it with your fingers, and your fingers are going to exert a force against it, basically a normal force. And then what we're going to have is, if we look at this book, you're going to have a normal force here due to your fingers and a normal force here. Each of these fingers, there's going to be a friction force. Am I drawing that? Yeah. Because it's trying to pull down, the friction force is going to act upward. This will be static friction. Now, if we look at this, we're going to figure out, I forget what we're figuring out, but I know we're given these two normal forces, and we can say X and Y. Doesn't matter because we're in static friction. So these forces are at most 6.6 newtons of force. And is what's shown, what is the heaviest that we can give if we assume that the friction has a coefficient of 0.9. So static friction forces are mu n, we know n. Rewriting this, we see that we have MAY is 2 times the force of static friction, 1 for each finger, minus mg. And because we're in static friction, that's 0. So 2 times the force of static friction is equal to mg. The force of static friction is mu n, so this is 2 times mu times that 6.6 is equal to mg. And what is the heaviest book? We want the weight, mg. So if mu is 0.9, the greatest weight that we could have is when it equals the maximum static friction force. So 0.9 times 6.6. So 2 times 0.9 times 6.6 is 11.8. So about 11.9 newtons. I think they're going to round it to 12. But yeah, so the key to this is, and the reason why I gave it to you, is a little bit tricky, because normally we're used to things being on a plane and their normal force being up and then their friction being one way or the other. But this one's turned 90 degrees. And the fingers have a static friction force because the weight of the book is falling. The static friction force is going to oppose the weight. Static friction's hard to do, but I like this problem. It's actually kind of a fun problem. All right. And then the last thing we have is we have a high Reynolds number drag force. And the force of drag is something called a drag coefficient divided by half, the density of the air or the fluid that you're in, the cross-sectional area, and v squared. Now, terminal speed is reached when the force of drag and the weight basically cancel each other out. So let's say that y is that way, but when MAY is 0 is equal to the force of drag minus the weight. Now we know the weight is mg and the force of drag is that. So we have FD is equal to mg, or all of this stuff is equal to mg at terminal velocity. So when this is terminal velocity, it's the only time it's true. Otherwise, we'd have to do some integration and stuff. We're told that the ball is 6.5 centimeters in diameter, okay? So when a ball is falling through the air, right, what the air sees is a disk. It sees a circle. projected at it. And a disk has an area of pi r squared, but d is r to the half. So it also has an area of pi d to the half squared. So our cross-sectional area is going to be pi d squared to the fourth, which is pi to the fourth. Our diameter is given as 6.5 centimeters. We need that in meters. This is 6.5 centimeters in meters. The density of the air is 1.2. The terminal velocity is 12 meters per second. This is in kilograms per meter cubed. And what else did we have? We want to find the ball's mass. So let's solve this for mass. And I'm going to erase a little bit of stuff so I can solve this for mass. And I wonder why they, oh, I'm, sorry. I don't know why they're assuming that the drag coefficient is a half. Maybe that's actually in your book. So we can assume that the drag coefficient is a half, which is a little bit weird, but CD is 1/2. I think that is actually in your book. So M is equal to CD to the half times rho of air times VT squared times A all over G, just divide by G. If CD is a half, this is a half times a half, so that's a fourth, times the density of air is 1.2, times terminal velocity squared, times pi to the fourth, times 0.065 squared, and this whole thing over 9.8. So what we get is 0.25 times 1.2 times 12 times 12 times pi divided by 4 times 0.065 times 0.065, and then divide that by 9.8, and I get 0.0146 kilograms, but in grams, that's 15 grams, which is what they took here. Yeah, I'm not sure why they're assuming that the drag force is a half, and I'm sorry, I should know that. So maybe I just missed it in your book somewhere, that for a sphere it's a half. I think I do remember reading that. But normally we're given, oh yeah, they say it here, the drag coefficient for a ball, a tennis ball, is 0.5. So they're using 0.5. Normally you're given a drag coefficient and it can actually be anything you want it to be. Here the drag coefficient is going to be a half. Sorry for not telling you all that. But yeah, it's actually just a plug and chug equation, to be honest. The only time the drag force is ever used is for terminal velocity, and you end up with this equation. And you're usually given the density, you're given the drag coefficient, and you're given the cross-sectional area, or you're given the diameter or radius or whatever. And then you either solve for VT or you solve for M. You're given one. Now this is high Reynolds number, meaning that there's low viscosity. It's easy to go through the fluid. If the fluid were like jelly or water, water actually is a high Reynolds. Something sticky that you were dropping through, you would be in the low Reynolds number. And when it's low Reynolds, it's basically beta B is the drag force. We won't deal with that, but the difference between high and low Reynolds is a high Reynolds number is a fluid that easily separates. And a low Reynolds number is something that has a lot of viscosity, it sticks together and it's hard to pass through. Anyway, so that is all of our homework. I'll try to get worksheets 1 or 3 and 4 and quiz graded, and I'll put your test scores in. I'm sorry, I've been lazy about putting them in since I know you know what you got. But I'll get your test scores in this weekend. And then we're going to cover chapter 8 next week. And I hope you all have a wonderful weekend and get your homework done. So if any of you that are still here have some questions, let me know. Otherwise, I'll see you on Monday. Thanks, guys. You too, Matt.